Hi, welcome back. Dr. P here, and we're going to continue talking about um, how chemical bonds form and also ways of representing chemical structures. So let me go ahead and share my screen, and we will go ahead and get started here. So this is chapter 1, lecture 3. And we'll look at molecular orbital theory. As well as some ways of representing chemical structures. I know last time we didn't get to molecular orbital theory, and that's because I felt like the lecture was going on a little long, but I will spend a little bit of time in this lecture to take a look at that. So molecular orbital theory we're going to combine atomic orbitals just like we did in hybrid atomic orbitals. But this time we're going to combine atomic orbitals from different atoms. And we'll end up, instead of getting hybrid atomic orbitals, we'll get new molecular orbitals. And the number of molecular orbitals that we get is going to equal the total number of atomic orbitals used. So we could do this for hydrogen. And we can look at our energy here, and we can have a 1s orbital from one hydrogen, another 1s orbital from the other hydrogen. Each has an electron. And when we combine them, well, our two atomic orbitals give two new molecular orbitals. They're going to be symmetric here, and that they're both the same distance from our zero energy. We'll call these sigma for the lower energy and sigma star for the higher energy. And we have two electrons, so we'll go ahead and put those in. And in this case, we have stuff in a bonding orbital. By stuff, I mean electrons. And up here, sigma star is an anti-bonding orbital. So if we were to draw pictures, it would kind of look like this, where these dots are the nuclei. And then we have a whole bunch of electron density that's like in between. This kind of looks like what our sigma system looked like. Whereas the antibonding orbital has our nuclei and then lobes going the other way. So we have in between, we have what's called a node, a region of zero electron density. So any electrons in an antibonding orbital would contribute to the instability of a molecule. So maybe it's better to say electrons in bonding orbitals contribute to the stability of a molecule. Electrons in anti-bonding orbitals do not contribute to the stability of the molecule. And we can do this for other systems as well. this is going to be especially useful for pi systems. In fact, that's one of the strengths of molecular orbital theory. Molecular orbital theory does a better job representing what's going on with pi systems, especially ones that are what we call delocalized. They're spread out, like in benzene. So valence bond theory and hybrid atomic orbitals are good for looking at sigma systems, and molecular orbital theory is better for pi systems, especially when we've got delocalized electrons. All right, so let's go ahead then and take a look at some ways of representing chemical structures. So we've talked about bonding, but we want to be able to draw things in different ways. And just as an example, let's look at acetone. So we have the chemical formula. In this case, it's C3H6O. But this doesn't tell us anything about the structure. Okay, it just tells us how many carbons, hydrogens, and oxygens we have. So we could draw something that indicates structure, like a Lewis structure. And again, you should take a look at the handout on drawing Lewis structures. This doesn't show geometry. It's also a little bulkier, and it's kind of hard to type this. So what is sometimes used is a condensed formula. And in a condensed formula, it's a chemical formula, but we lump together the bits. So we have CH3, which is this guy here, CH3. And then we have our CO in the middle. We understand that to be C double bond O. And then we've got another CH3 on the other side. C and 3H, CH3. Okay, so this hints at the structure, but doesn't explicitly draw it out. An expanded formula has some bonds shown. So we would do CH3, CO, CH3. So we'll just say here, some bonds shown. All right, now there's more. There's a bunch of different ways. One way, and it's actually the way that chemists usually like to draw things, is with bond line or skeletal structures. And in this case, there is our acetone. Now, there are some things to note about this representation. Every time we have a corner, a vertex, or an intersection of two lines, or ends of lines, we have a carbon present. So for example, looking back at the Lewis structure, we can see that at one end we have a carbon with 3 hydrogens bonded to a carbon, double bonded to an oxygen, bonded to another carbon with 3 hydrogens. There's that first carbon right there. That carbon there is that carbon there. And then in the middle, we've got an intersection, carbon, double bond to oxygen. So there's the carbon there, and that carbon right there. So you'll want to get used to wherever you've got corners, ends of lines, intersections, those are carbons. We also have what are called implicit hydrogens. So notice that in the Lewis structure, I've drawn out the hydrogens. Here, they're not shown. They are implied. We understand that that's a carbon at the end and is bonded to one other carbon. So it must have 3 hydrogens on it because carbon forms 4 bonds. One's going to carbon, the other 3 have to be to hydrogens. Same with this carbon over here. The carbon in the middle doesn't have any hydrogens because it has 1, 2, 3, 4 bonds. We count the double bond as 2 bonds. Lone pairs are often not shown. So you can see here, I haven't indicated the lone pairs like I did up here on my Lewis structure, but it does show the geometry. So we can see that my carbon bonded to 3 things is going to be sp2 hybridized. And this is indicating it's a trigonal planar-like shape. It's not quite as sort of squarish as the Lewis structure. All right. We can do 3D structures as well. In particular, what's used is the wedge and dash, formalism. And if I wanted to draw this out here, I could. So now I'm showing my hydrogens, where they are in space. And again, the wedges are coming out towards us. We would say they're coming out of towards us, out of the plane of the paper. Dashes are going away from us, back behind the plane of the paper. Everything that's just a line is in the plane. Now, one thing to note is that combinations of these are often used. For example, we could have so I've drawn my acetone. I've got my lone pair, like my Lewis structure. I've got my center carbon not labeled as a carbon. That's like my bond line structure. I'm indicating my trigonal planar geometry, like my bond line structure. But then I've got CH3, like my expanded or condensed formula. So you will want to get used to representing chemical structures in different ways. And it's definitely something worth practicing. All right, so that just about wraps things up. And I'm going to stop sharing. Thanks everyone for tuning in. And we will start with chapter 2 in the next video. Okay, bye.